So thanks a lot for coming to this webinar on simple private transactions on a blockchain. I'm Jeff Gillis from ConsenSys. The Adhara team is going to be hosting this and delivering it, led by Peter Munnings. They launched the Project Khokha in South Africa, which they will tell you about. And it's going to be about the state of the art of privacy. You'll learn a lot. It's not how to set up privacy in a blockchain necessarily, but you're really going to learn a lot about how a blockchain works and how transactions can be made private and kind of the latest technology around that.
Great. So let me just start off with Adhara. What is Adhara? We are a company that was launched by ConsenSys. ConsenSys are our seed funders. And we do real-time solutions for multi-currency global liquidity management, so FX, international payments, all based on tokenized money over smart contract-enabled blockchains, essentially. So we work with banks, we work with central banks, we work with e-money providers, and we take cash in bank accounts, for example, and we put it onto blockchain. So we're very, very interested in how you do transactions on blockchains with real money. And we're also interested in the regulatory requirements around that, and a lot of that is to do with privacy. So we spend a lot of our time looking at privacy solutions, and that's what I want to do today. We're going to be doing a poll during this, and the question on the poll is what kind of data is important to keep private. Jeff's going to pop that up right now. Can
everybody see the poll?
So I can see the poll, so I can't vote.
Panelists can't vote. So please shoot your vote in there now, and we will end it in about 45 seconds, and then we'll look at the results, and Peter can talk to that.
Great. So we're going to be looking at what is transfer of value, what is transfer of value on the blockchain specifically. We're going to build on these, and then therefore what is simple private blockchain transfers. And then we'll have a look at some of the work that's going on at the moment around Peterson commitments and related technologies. And then I'm going to give you a couple of real world examples, and then we'll talk about some of the other product teams within ConsenSys and what they're busy with.
All right, Peter,
so if we're looking at simple private transfer.
We have about 70% voted, so I'm going to close the poll and let you talk to the results, okay?
All right.
All right, great. Everybody get your vote in last seconds here. All right, there we go. Poll is done. Here are the results.
All right, so there we go. Personal data, really, really important to keep that private. The second one looks like a exact tie between balances and transaction amounts. Brilliant. So we'll cover all of that today, pretty much. All right, so let's start off the basics. What is a transfer? And what we want to do is, Bob over here has $100, and he'd like to get it across to Alice. So in some way, he'd like to move that money from his account or his control or his wallet across to Alice's. Now, a physical transfer is easy to understand. It's also the basis for pretty much everything else that we have today. So if Bob has a $100 note in his pocket, he takes it out and he hands it over to Alice. So that's very easy to understand, but there's a lot of very important principles in there. One, Bob doesn't have control anymore of it. It's now in Alice's pocket. She has control of it. Bob can't spend it. Alice can spend it. So those are important principles. Now, the value transfer is the movement of the $100 bill, but there's other data that is indirectly linked to that value transfer. So maybe Bob introduces himself to Alice and says, "Hi, I'm Bob." She says, "Well, I'm Alice." And he says, "I'd like to buy your secondhand phone for $100. And she says, "Okay." And that's the context of why he's giving her the money. So it's never outside of any kind of context. And they may also want to keep, as we've seen now, a lot of that information private. So the names, the reason for the transaction, the asset that they're trading, the amount that they're trading that asset for, etc. And then the actual movement of the money is the transfer of value. If we look at a digital transfer, we think of it in accounting terms. And so Bob has 100 in his digital account. And from an accounting perspective, we do a debit on his side of the book. So we take $100 off, and we do an equal but opposite credit on Alice's side. So she gets 100, and Bob ends up with nothing, and Alice ends up with the 100. If we want to think of it in terms of data, we have an initial state for this data set. We do the transfer, which is the debit and the equal but opposite credit. And then we have a final state, which is where Bob's got nothing and Alice has got the 100. So these are all really important concepts, and they become really important in the real world. Now, a real world example that we've worked on a couple of times is, so what we saw now is a really simple transaction. And if we have a client at bank 1 and he needs to pay a client at bank 2, we can debit the client's account at bank 1, but bank 1 can't credit directly the account of the receiver at bank 2. They have to go through an intermediary, which in most countries is a central bank. And the central bank would debit the bank 1's account at the central bank and credit bank 2's account at the central bank. And so it becomes a fairly complex process with numbers of ledgers involved and lots of messaging in between to make sure that that event happens. And so banks themselves are looking at simplifying that process of saying, what if we put this onto a single ledger? And we know that it works on a digital ledger, a blockchain-based ledger. The central bank can still have oversight over that, but now it becomes a simple case of debiting the client, the sender's account at bank 1 and crediting the receiver's account at bank 2. And this is a very real world example. This works. Just while we're going, there is an opportunity if you want to ask questions, and there is a team on standby who will answer those questions. So let's have a look at what a transfer is on a blockchain. We know that a blockchain is a set of nodes that are distributed, they are connected to each other, they keep in sync with each other through a consensus mechanism. And basically we take that same transaction between Bob and Alice, so the digital transaction, 100, Bob starts with 100, he does a debit on his side, a credit on Alice's side, and she ends up with 100. That same transaction, all of the state, all of the transaction itself is communicated to all of the other nodes. All of the other nodes stay in sync through the consensus mechanism, and everyone has a copy of that transaction. So everyone can see exactly what happened on that transaction, and that's a really important principle as well on a blockchain ledger. So every node is a copy of all the states and all the transactions. All the transactions can be verified, which is really important as well on all the nodes. And there is no dependency on any specific node on the network. So all the nodes are equal, certainly on an Ethereum network, and there's no extra dependencies. The idea with a blockchain network is you can add and remove nodes, and there's no reliance on any specific node on that network. So let's have a look at privacy now. We're going to dive into privacy. We've had a look at transfers. We've had a look at what a transfer on a blockchain looks like. And now what we're going to do is dive into how do we make it private and simple. And there's many examples of data that needs to be kept private. For the purposes of this webinar, we're going to split them into 2 buckets. And the first bucket is any data that does not affect the stored value on the blockchain. And we saw things like personal data in the poll, GDPR compliance. The fact that my name is Peter has no impact on any transaction I do in terms of the value, but I do need to, for purposes of KYC or anti-money laundering, I do need to put that kind of data into the transaction. So my name, my address, some kind of reference to my ID, for example. And then there's data that does affect the stored value on the blockchain. And it's important that we keep these things separate because the way we handle privacy around these 2 things is quite different. Let's have a look at it in a different way. So let's say Bob, instead of sending Alice money, he took a photo while he was on holiday at the beach and took a photo, and he decided he wanted to send it to Alice. So he wants to send Alice his picture. He sends it across. Now, what happens typically is they both have a copy of that picture of the data, and they can both send it on to other people. And this is fine for most shared data. But when it comes to value in a shared network, like a blockchain network, it's not fine at all. So if we have a look at the value, the data that affects value, we see that when Bob sends the $100, he cannot retain a copy of it. Both he and Alice need to be 100% sure that the money moved. It wasn't copied, it was physically moved from Bob's account to Alice's account. And it's not just Bob and Alice that need to know that. Everyone on the network needs to know that. And the reason that everyone needs to know that is because this transaction doesn't happen in isolation. They are not passive observers. They're actively involved in the ledger themselves, and they may participate in future transactions. So if Charlie receives money, or Bob tries to pay Charlie with the same 100, Charlie needs to be sure that Bob no longer has access to that 100 and Alice does have access to the 100. This becomes really important when you start looking at how do we make these things private. Let's go back to our example with the debits and the credits. Now, data in this situation that does not affect the stored value is things like name, the fact that Bob was paying $100 for a second-hand iPhone. Data that does affect the stored value, so that's value transfer, is obviously the transaction amount itself, and then the initial and the final balances. Those are all intrinsically involved in the value that is stored on this blockchain network. Now, there are many ways to make data private on the blockchain, and some of them work really well for data that doesn't affect the value, and others work well for data that does affect the value. So the first thing we can do is obviously limit who has access to that blockchain. And the Kaleido team are with us here today, and they're going to talk a little bit about this at the end. They have a lot of really good tools for limiting who has access to a permissioned blockchain network, and that's kind of your first set of defenses, if you like. So we're going to limit who is allowed to actually transact on this blockchain network. The second way we could do it is to put the data onto a private channel between only the nodes involved in that transaction. And we have many examples of that: Whisper, Swarm, Constellation, or Tessera, and Quorum now, and Kaleido off-chain communication. So there's lots of ways of setting up private channels. The Pantheon guys are also on the call. They're going to talk a little bit about some of their sidechain work that they're busy with, and that's another form of doing a communication just between a set of actors on the network, a private channel, if you like. We can send the data via an unrelated channel, so completely off-chain with some kind of reference back to transactions, and we can send some data via email, for example. We could send it by secure email, only to the specific counterparties who need to see it, and reference that back to the transaction. We could also encrypt the data in the transaction. The only problem with blockchain networks is that they're immutable. The transaction stands forever, or as long as the ledger is up. And that's generally not a good idea, because we know that people can eventually decrypt data. So it's not a good idea as a standalone method, but it certainly works really well in combination with some of these other methods. So what I'm going to say up front is that data that does not affect the value, the balances, the transaction amounts, anything that doesn't affect the value transfer, so all the personal data, any metadata associated with that transaction. Obviously, once we've secured this permission, and we're speaking specifically about permission networks, we've secured the network, we know who's on it, but any data that is metadata that is related to a transaction but doesn't affect the value of the transaction or the value of the whatever value is stored on the blockchain, we put that in a private channel, and we can encrypt that for good measure. Most private channels have built-in encryption techniques or encryption tools, and that's a really good way. So Bob's full name, Bob's address, the fact that he's buying a second-hand phone from Alice, that doesn't have to be distributed across the entire blockchain network. That can be just put onto a private channel between Bob and Alice, and that's a really, really good way of solving that problem. And so non-value related data on a blockchain, the best way to do it is to pop it on a private channel and communicate it just between the counterparties who need to see that data. The rest of the network just has no idea that it's even there. There's no way that they can decrypt it, because they physically just don't have access to that data. Now, data that does affect value, or the balances on the blockchain, this is a bit more interesting, and I want to explore a little bit around this. And this is really where the meat of the talk is today, the webinar. A transaction, every transaction in terms of the value of that transaction, the balances, the transaction amounts, every transaction is linked to the one that happened before it, and it will be linked to the one that happened after it. So transactions are linked together. Therefore, it's very difficult to use private channels to do value transfer or to keep value transfer private from the rest of the network in a simple way. And I'll explain why now. So let's extend our example. So we see here that Bob did a debit on his account and credited Alice's account, or wallet, if you like. And then Alice now has 100 in her wallet. That's the state of her wallet at that point. Alice can now debit her account by 75, credit Charlie's by 75, so do a transfer of $75 from her account or her wallet to Charlie's. She'll end up, this new state is 25, and Charlie's state is now 75. So Charlie needs to know a couple of things. He needs to know what the state is in the network in order to know that the transaction from Alice to Charlie is valid. And in very simple terms, he needs to know that Alice has the money to pay him. He also needs to know, for example, if Bob was trying to pay him and Bob had nothing to pay with, that would be an invalid transaction. So he needs to know the state across the whole network in order to validate that transfer is a valid transfer. Now, if Bob and Alice were on a private channel that Charlie was not privy to, then knowing the state becomes complicated. It can be done, but he would need a notary service or some other way of being assured that that Alice has the money to pay him, has enough to pay him. So what we're doing is we're introducing another level of trust onto the network. It's no longer a trustless environment. And we also, one of the side effects of this is that we reduce resiliency and we introduce points of failure into the network. So it's not a good idea, and it's actually really, really hard and complicated to move money from private channels to private channels on a blockchain network. It also gets complicated because the more actors or nodes we add to the network, the more additional layers of complexity there are. Potentially, for every new actor that you add, you're going to need to add new private channels. You need to add new notary services or new trusted services on this network. And then synchronization to the existing states becomes really complicated. As a new node is joined to the network, it needs to decide what it can synchronize to and what it can't synchronize to. And that all adds additional layers of complexity. So if we go back to our example, what we need to do somehow is remembering that these values are stored across the entire network. So in a visible network, something like the public Ethereum network, everyone can see all of the values. Now we know that people have built other networks where these values are hidden away. And what I want to have a look at now is how do we make private the balances and the transaction amounts, because that's a really important kind of part of this. So what I'm talking about here is that even if you are a valid authenticated node on the network, so you're on the permission network, you've come through all of the authentication in order to be a valid participant on the network, you are storing values on your node for all the transactions on the network, and you're validating that all those transactions are valid transactions. And the most basic validation is that if someone has a balance, they receive an amount, that old balance plus the amount is equal to their new balance. Even by having all of that in place, you still should not be able to see what the values are in a truly confidential network. So what we want to do is to take all the values that we understood and were kind of clear and hide them away. So I'm just going to blow up one of these nodes so that you can see it clearly. So basically, we saw that originally Bob had 100. He sent 100 to Alice, and then she ended up with 100. But what if we could create a network where Bob has some kind of randomized version of his 100. He sends some kind of randomized version of his 100 to Alice that doesn't make sense to anyone else on the network. And he ends up with a random balance that no one can understand or figure out what the actual balance is. This would be great, because then if we could do this, then no one could see what the values are, but everyone would have access to the values like a true blockchain network. Now, it sounds nonsensical to put it like this, but actually, this is the very best way to solve it, and I'll explain why very simply. So from Bob's perspective, he obviously knows that he started with 100, he transferred out to 100, and he has nothing at the end. But he can't see what Alice started out with. So when he looks across at Alice's balance, he just sees a random number. But he does know that he's sending her in this particular transaction 100, so he knows that she will receive 100, and she ends up with some random number or some, let's say, a very special kind of hash rather than just a random number, a very special kind of hash afterwards. From Alice's perspective, she looks across at Bob's account and she sees he started with a balance that she doesn't know what it was. She knows that he sent him 100 because she received 100, so she knows what that number is, but she has no idea what Bob's final balance is. It's unknown to her. From Charlie's perspective, he can see that both Bob and Alice had some kind of opening balance, that they did a transfer. He obviously knows, he can see that what Bob sent was what Alice received. So the debit matches the credits, equal and opposite. But they end up with some other balance. And that's Charlie's perspective. So he can see that something's happening on the blockchain, but he has no idea what it is and who's sending who, how much money. Now, I want to introduce Reino. Reino Bays is going to take us through Pedersen commitments, because Pedersen commitments are these really special kind of hashes. So is the doctor in the house?
Hi guys, thanks Pete, and hello to everyone. I hope you can all hear me.
Good, nice and clear.
Awesome. All right, so what we have here on this slide is essentially two different views of the same thing. So we have the actual amounts on the left-hand side, and then we have the shielded amounts on the right-hand side. So we don't want anyone to see what we have on the left-hand side, but we are going to share with the whole blockchain network the shielded values. Now, the way we get from the left-hand side to the right-hand side is by executing some kind of algorithm by using those actual amounts as inputs. And by doing that, we convert them into what we call commitments. So now you might think, what the hell is a commitment? Let me just spend a minute or so to explain that a little bit more. All right. So if I look at the Wikipedia page, which actually gives quite a nice explanation, a commitment is just something that allows you to commit to a value while keeping that value hidden from others. Now, obviously, if you've committed to that value, it means that you can't change it afterwards. All right. There are actually many different types of commitments, and they all have different properties. As an example, you could simply use a SHA-256 hash, which is a very well-known and often used hash function, and you can just use that to create a commitment. We can't use that in our scenario, but let's just take a minute to think about how that would work. All right. So in our scenario, let's say I have a starting balance of 8 tokens, and I want to send someone 5 of those tokens. Then I need to end up with a final balance of 3 tokens. So if I wanted to do this particular transaction in a shielded way, I would then, using the SHA-256 as our commitment function, have a balance that is equal to a hash of 8. That would be my initial balance. And then the amount I would be sending would be a hash of 5. And then what we'd like to have then is that the final balance needs to be a hash of 3. However, unfortunately, if we use a hash like the SHA-256, this will not be the case, because a hash of 8 minus a hash of 5 will not be equal to a hash of 3. And the reason for that is because this type of hash function is not what we call homomorphic. Okay, homomorphic is just a mathematical term that describes this particular property. All right, so if we can just move to the next slide. So in our scenario, we use a different type of commitment. So we don't use the SHA-256 hash function. We use what is known as a Peterson commitment. And Peterson commitments are special because they are homomorphic. Now, this means that you can choose to either do the math on your values first and then commit to the final answer, or you could commit to the input amounts, the individual amounts, and then do the math on the commitments. And you will, in both cases, arrive at exactly the same answer. Just move on to the next slide, please. All right, so Charlie, who has no knowledge of the underlying values, can still validate that Alice has the correct balance because he knows and he can check that her balance was calculated in the correct way. All right, so in other words, by committing to the amounts first, submitting them to the network, allows the whole network to check that the correct steps have been taken to update someone's balance. And this can happen without revealing any of the actual amounts. All right, now on the next slide, we're just looking back at a previous example. Now, the important thing here, as Peter's mentioned, is that for any single transaction, the commitment that gets added on the receiver's side, so the commitment that gets added to the receiver's balance, has to be exactly the same as the commitment that gets subtracted from the sender's balance. And if we can be sure of that, we know that the sender and receiver balances go down and up respectively by the same amount. And therefore, the value has moved from sender to receiver and no new tokens have been created in the process. All right, now before we go on to the next slide, some of you may have realized that there's actually quite an easy way to cheat the system, at least up to this point, as we've explained it. So the first problem is that when these amounts are hidden, we have no way of knowing if someone is trying to send a negative amount. And so sending a negative amount is problematic because as sender, if I send a negative amount and my balance gets updated, the mathematical operation would be a subtraction of a negative amount, which would actually result in my balance going up. So if I can do that, I can actually steal money from other people without them really being able to do anything about that. So obviously that's not so good. The second problem is that we have no way of knowing if someone has spent their entire balance and that they have no money left or not enough money to do a particular transaction. So on the next slide, we show here basically the reason for this is that you cannot, by simply looking at a commitment, determine whether it has or is a positive or a negative number. But there is this special thing called a range proof that we can use to prove to the whole network that a commitment is positive. And we can do this without revealing anything else about that value. So basically, you'll have this Peterson commitment. It looks completely random. And what you can do is you can prove that that random number is positive. All right. Now, in fact, we'll need two of these range proofs. The first one will be for the amount that you're transferring. We need to show that that's positive. And that essentially just fixes the direction that the value is moving in from sender to receiver. And then the second one is to prove that your final balance is positive. So that means after subtracting the amount that you're sending someone, you have either 0 or more tokens remaining. And the beauty of this is that all of this can be verified on-chain, which means that the whole blockchain can very easily be convinced that these proofs are valid. All right, so if anyone has any questions about this, please put them in the Q&A. I'll try and answer them. If you want any more detail on that, yeah, just put them in the Q&A section. And yeah, handing back over to you, Pete.
Thanks, Rainer. So it really is simple confidentiality. It's scalable. So when you add another node to this network, the node will synchronize just like a normal Ethereum node on the public network does. It can see the current state. It just doesn't understand exactly what that current state means, but it knows it's valid. And it can immediately begin participating in new transactions from anyone on any node on the network. It's easy to share the actual amounts. As we've seen, we have lots of options for private channels, private encrypted channels. And in order, for example, to share the amount that I'm sending, I create the commitment for that amount, and I send the actual amount via a private channel only to the person who's receiving it, or in the case of a regulated environment, to the regulator as well if they need to see that. And then the actual amounts can be very, very easily validated against the Peterson commitment, which is available publicly on the blockchain. And as Rainer has pointed out, balance updates can be verified by everyone on the network. It's very simple maths. It's a number plus another number is equal to the third number, and we can do that. And that proves, as long as the credit matches the debit matches the credit, rather equal and opposite, we can prove deterministically that no one can possibly create or destroy value on the network in any transaction. And the technical term for this, for any kind of ledger operation where this is in place, is called mass conservation of value. So basically, if we think back to our original ledger, we had $100 on there. That $100 got moved from Bob to Alice, and then 75 of those got moved to Charlie. 25 remained with Alice. At any point, the state of the ledger was $100 spread across a couple of wallets. We can prove that this is true. This is mass conservation of value. All right, so that is a simple private transfer on a blockchain, but it's not just theory for us. We've done it a couple of times. And Project Khokha was probably the most interesting one because we applied exactly this, and we'll go through it. Project Khokha was an interbank payment proof of concept run by the South African Reserve Bank. We did it between January and March last year. These were high-value payments that were moving between banks for settlement between banks. A little bit of background to Project Khokha. So we built Project Khokha off the work we did in Project Ubin in Singapore with the Monetary Authority of Singapore in 2017. In Project Ubin, we use zero-knowledge proofs on quorum to provide confidentiality. And a zero-knowledge proof is a little bit more complicated, but effectively gives you very similar results to what Pedersen commitments and range proofs do. In Project Khokha, we wanted to extend the work by building a real-world blockchain network and run real-world volumes through that network. And that really was the catalyst for saying we need to look at something other than zero-knowledge proofs. Zero-knowledge proofs are great, but they are computationally expensive. It's really complicated and expensive to verify them. And we needed to verify a lot more transactions than we could using zero-knowledge proofs at the time. And so we looked around and we implemented these Pedersen commitments with range proofs because we needed to maintain the same level of confidentiality that we had achieved in Ubin. This was the actual infrastructure that we used. So there were 7 commercial banks, 1 central bank. ConsenSys were running a number of validating nodes. We were running a quorum network using RBFT as the consensus mechanism. Some of the banks were using the on-premise, their own TIN on-premise, so their own VMs running in their own data centers. One of the banks used the private Azure cloud. One of the banks used AWS, and a couple of banks used Azure. So it was a completely heterogeneous environment, different banks running different physical hardware, all running obviously quorum and all using RBFT. So the aim was real-world infrastructure. We had 7 commercial banks with a complete mix, full production volumes. We were required to do 70,000 transactions, completely shielded, completely distributed in less than 2 hours. We managed to achieve it in 90 minutes. And for those of you using range proofs, that is less than 2 hours, just so that you know. We needed full confidentiality. We implemented Pedersen commitments and range proofs. We needed settlement finality, which is one of the principles for financial market infrastructure, which was one of the principles we needed to implement on this project. And RBFT gives you settlement finality, which is great. And then obviously the SARB needed oversight without being operationally involved in any of the payments. And you get that out the box with the blockchain network. This is actually a screenshot from the solution we built. And you can see this is a bank called ABSA. But for the sake of argument, it's the red bank. It has red in its logo. And we can see that any transaction where ABSA was involved, they could see the transaction details. Any transaction where ABSA was not involved, they just simply couldn't see anything. So they saw that a transaction happened at a particular point in time on the network, but that was it. It was a completely confidential network to them. So anything where they're involved, they saw the amount. They obviously knew their own balance all the time, but they couldn't see any other bank's balance. Project Khokha went on to win the Best Distributed Ledger Initiative from the Central Banking Publications in Singapore. And it was great to see it win this very prestigious international award for the Best Distributed Ledger Initiative for a central bank. And that was last year sometime. All right, I'm going to hand on to the Pegasus team. So if one of them wants to pick up and just talk around what's happening with Pantheon. We love the Pantheon team. We work very closely with them, and we really enjoy what they're coming up with. Let me just switch my mic off.
Thanks, Peter. And hi, everyone. I'm Grace Hartley. I'm from the Pegasus team, which is the protocol engineering group at ConsenSys. We are a 55-person team now dedicated to building Enterprise Ethereum. I'm just going to spend maybe 2 minutes talking about our Ethereum client, Pantheon. Pantheon is our Apache 2 licensed Ethereum client written in Java. We launched at the end of last year, so late October, with our public chain. And then now we, as of 2 weeks ago, have launched our enterprise grade features, our consensus algorithm, IBFT2, and our permissioning features. We will also be launching our privacy features at the end of next month. We are unique because we have a very robust R&D team that is also helping research projects like Peter mentioned earlier, sidechains, ETH 2.0, sharding, database integration, et cetera, that we all hope to eventually integrate into our product Pantheon. in the coming months and years. Do you mind going to the next slide? So just to tell you a little more about Pantheon, so we have built it to have secure permissioning, stable consensus, dependable privacy, and familiar tooling. So secure permissioning means that we have account and node level whitelisting. And then at the end of next month, we will also have smart contract-based permissioning. And as kind of mentioned throughout this, this will restrict network membership to the correct enterprises, which will be highly beneficial when you want that kind of private network. Stable consensus. So we have an improved version of the Istanbul Byzantine fault tolerance that we've built to be more fast and reliable with sending transactions. We're actually hosting a webinar on March 26th that has that will kind of go into consensus algorithms and then why Pegasus decided to implement IBFT 2.0. I will add the link to the chat at the end of my session. So if you all are interested in that topic, please go ahead and register. Dependable privacy is our other feature. So we like to enable off-chain private transactions to prevent double spend. This will be implemented in our release, as I mentioned, next month. And then familiar tooling. So we have Java-based tools because we're written in Java. We think that's very interesting for enterprises and has a large developer community. We have cloud-based tools, so Azure, Kubernetes, Docker, etc. And then Ethereum tools, so Truffle, Lethio, MetaMask, you can also use on Pantheon. I know I kind of flew through that quickly, but I'll pass off to Nick. Please go ahead and ask any questions in the chat you might have.
Program director.
Can we get, awesome. Okay, so my name's Nick Gasky. I do client and technical enablement at Kaleido, and just gonna give you a quick rundown of what Kaleido is. So it's a full stack cloud platform for building these consortia permissioned enterprise grade blockchain networks. And one of our sort of our shining ethos, so to speak, in Kaleido is this concept of radical simplicity. So truly in a matter of minutes, you can deploy your own bespoke blockchain network running either the Geth client or Quorum with accompanying consensus algorithms. So it's very, very simple and streamlined to quickly iterate through development cycles, user acceptance testing, and gradually increment your way to a proper production caliber solution. So this morning at South by Southwest, we just announced support for Microsoft Azure. So we're delivering these multi-cloud hybrid borderless blockchain orchestrations. So now you can leverage your existing business processes and your application stacks running in your trusted cloud provider, and those can easily integrate onto a Kaleido platform with a single unified experience. So truly this concept of borderless. As you're building out the consortia, obviously you want to onboard subsequent organizations, your business partners. And what we allow you to do is have sort of this inherited or access control and governance. So you as the founder of the consortia, a system administrator, you can extend or rescind admin level permissions, and you can have sort of a baseline consortia with different organizations and different parties having different permissions on the network. One thing that we've realized as we've built this product and this platform is that the chain itself, the actual blockchain layer, is a really small piece in the broader apparatus of what comprises a proper bona fide solution. So we've introduced a marketplace, hence the term full stack I mentioned at the beginning. And this is comprised of a library of ancillary chain layer services, third-party solution accelerators, and then some of those native cloud services that you get from an AWS or an Azure. Things like KMS, log streaming, the ability to back up private communication streams, et cetera. And our engineers at Kaleido have actually done some proprietary and really, really unique things. One example of a Kaleido service, one of those ancillary services, is the ability to tether your private state information up to a public Ethereum network. So in these private networks, we use the quicker consensus algorithms that are reliant on private keys and digital signatures. So to prevent, the event of those keys getting compromised and possible collusion and historical rewrites, we allow all of the nodes to agree on the current state of the chain, and then they're all going to collectively sign over that state, hash, block number, etc. And that transaction gets aggregated and pushed up to a public Ethereum network. So this gives us that historical finality and collusion resistance. And then let's just take a look at the next slide, if we can. Awesome. Okay, so this sort of gives you a peek at what the full stack architecture of a proper enterprise solution would look like. And we see at the bottom that, you know, the chain layer is a really, really small piece. We have all of these different things that we need. We need enterprise identity, right? We need some methodology to bring in these trusted PKI identity schemes and underpin organizations and memberships with X509 certificates. We need a way to transact anonymously on the network, right? Perhaps quorum and private transactions isn't enough. We need to use ID masking and HD wallet, right? So that we can't be authoritatively identified. And then there's just a library of other things that we need. We need IPFS nodes for, you know, off-chain file storage. And in Kaleido, we're able to leverage sort of the richness and robustness of ConsenSys at large by integrating a number of the wonderful ConsenSys spokes and their solutions. So some examples of those are Viant for turnkey supply chain solutions, or Open Law for those legal agreements where signatures and acceptance actually become on-chain transactions and invocations of smart contracts. So we see that this is a sort of a big, very expansive layer of pieces that comprise you know, an enterprise grade solution. And at Kaleido, we're creating and building a single unified experience to quickly and rapidly get to sort of a deployment point where you can actually realize value from the blockchain.
Great, thank you very much. Thanks, Nick, and thanks, Grace, for that time. As you say, we work extensively with the Pantheon team, and we have done we've had a number of interactions with the Kaleido team, both great teams, and both building some really good things, and looking forward to seeing how those progress into the future. Jeff, I'm going to hand back to you. I'm not sure now how we do the questions, but I'm assuming you do. So we have about 15 minutes that we can open it up for questions.
Yep, that'd be great. There's one in the Q&A for Pegasus. Nick, are you able to see that? I'm sorry, Grace, on Pantheon, is there any documentation about the smart contract-based permissioning?
Yes, I see it. As of this point, it'll be available with our release in April, because that's when it will be released as a part of Pantheon. I can add you to our mailing list and send you the documentation once it's ready.
Great, thanks. Woody had another question. Peter, would that be one for Adhara?
So the question is, can you talk about any messaging platforms communicating between nodes, public and private context? So I'll give you a very quick answer, Woody. So in terms of messaging platforms, obviously Whisper has been around for a very long time. It's a messaging platform that runs on Ethereum. It's been part of a number of clients for a while. And Swarm obviously now has a number of messaging abilities. We are currently working quite hard using Swarm, specifically using postal services over Swarm. I'm going to leave it on to, I mean, there have been others. Constellation, for example, was effectively a messaging system between nodes. Kuni, Rainer, do you want to add any specific detail to that?
No, I think you covered it well, Pete. There are quite a few different options for you to use, and it will probably base on or differ on the use case that you want to solve for. So Pete mentioned a couple of great ones.
Good. I see there's another question for Kaleido.
Yeah, I can answer that. Yeah, so the beta does end at the end of this month, but what we've done in Kaleido is we've created some really logical tiers, right? So we have a starter plan that will be perpetually free, and then we have business, team, and enterprise. So as you're building out and developing your blockchain solutions, you can gradually increment through these different plans and grab the ones that you need. So it's a software as a service model where you're paying, you know, hourly costs for runtime of nodes and services. And you can grab and choose any of the features that are going to comprise your solution. As we have released our support for Microsoft Azure, we're also releasing continued improvements for developers, whether that's using our Kafka-backed ETH Connect layer, making it very easy to talk to the blockchain, not having to use Web3 client libraries. And we're also continuing to add new services to the marketplace that are always going to be free to try with the starter plan.
Great. And then I see there's another question for Kaleido.
Building a hybrid chain. Yeah, so Kaleido is really flexible, right? I mean, industry solution or use case aside, Kaleido is a very logical, flexible platform for anything that needs a private or permission consortium model. The one really powerful thing that we have, and that I've spoken to a number of times, is the concept of this marketplace, right? Which is a library of these services, solutions accelerators, and cloud integrations. So you have at your beck and call, very easily accessible, a number of these core components and, you know, applications that you're going to need to build out a bona fide solution. So I think the use case is less of sort of the identifying factor. It's whether you need a lot of the things that private permission networks provide, whether that's, you know, privacy for one, but perhaps more importantly, the ability to quickly scale, high performance, throughput, and, you know, this extensible configurability. So there's a question in the chat about you don't need Web3 to integrate to read on-chain data. What we've done with that service called ETH Connect is it's an abstraction of the core Ethereum JSON RPC API. So this Kafka-backed ETH Connect layer actually handles all of the Ethereum nuances. So it's going to take care of RLP encoding, nonce management, source code compilation, what have you. And then using Kafka, this is going to provide, you know, reliable delivery, and it'll also account for sudden surges or peaks, you know, in your workflow. So it'll deliver transactions into the network at the optimal rate and provide you guaranteed delivery to the Ethereum network.
Peter, there was a question in the chat. How is SARB supervising the system? Do you send it clear text values of transactions by some external means?
So I think Connie did answer that. So it was Victor who asked it, and basically I'll just cover it here. So there was a couple of things we do, but in order to interpret a commitment, you need the underlying value and you need what's called a blinding factor. And so those two things were shared with the central bank, with the regulator, for all the transactions. So they actually had a visibility on all balances and all transaction amounts on the network because they were given the blinding factors and the values as well. So they could confirm the commitments that were on chain, and they could also observe the values that were moving. What was interesting about it, though, is that unlike a centralized system, if they were not online, if their node was down, if they were not available, everyone else could carry on transacting. And it was when they came back up, they would resynchronize with the network. They would pick up all of these values and blinding factors, and they would be able to, once again, validate that everything was correct on the network. So they were able to run their oversight role without having to be involved in their operations.
Thanks. It looks like we're through questions. Anybody have any last questions? Like there's one more coming in.
So Woody asked the question, any counterparts to modeling language like Hyperledger? It's gone. All right. So Jonathan Finberg, I've seen several live streaming protocols being developed on blockchain. Is it feasible with today's throughput? Can the blockchain handle its scale, or do we have to combine protocols? So I'm not sure I fully understand that, but I think the gist of it is that obviously if we're going to be shielding transactions and we need to verify additional pieces of information around there, that's going to take computational power, and the throughput's going to slow down. So Jonathan, to answer your question, we work a lot in the settlement space, which is typically not huge volumes of transactions. And we haven't come across a situation where we can't handle the volume of transactions that's coming through. And we're seeing that both the throughput on the network in general, as well as the speed of the algorithms, the curves that are being used are being optimized, the elliptic curves. And so we're seeing improvements literally year by year. So to give you an idea, when the Zcash team started their research, it was probably about 3 years ago, or maybe 3.5 years ago, it would take about 45 minutes to generate a zero-knowledge proof. That came down significantly, and when we did 2 years ago, when we did the work with the MAS, we were generating a proof in roughly 4 seconds. Now we can comfortably do around 20 transactions per second, and we haven't really pushed it because we've been doing a bit more research. But you can see the kind of the throughput increasing, and at 20 transactions per second, that covers many different settlement systems.